C sub n. And hold on, what does C sub n represent? It's not a constant necessarily. It is generated into a constant, but what is it based on? N. You plug in n. It can be any formula with just n in it. It's some impact of n on, and then what's it multiplied by?
X minus h
to the n, and then it's the summation as n goes from 0 to infinity. Exactly. So anything that fits that form is considered to be a power series. The key thing we're going to study is for some values of x, these series will converge. For some values, they won't diverge. Exactly, won't converge. They'll diverge. Sometimes some power series will converge regardless of what x is, and sometimes the power series will converge regardless of x is. There's 4 different pieces here. Actually 3. So sometimes, always, and never are basically our outcomes here. So in your examination, I think you were supposed to look at 9.5. You're supposed to look at 9.5. In your examination of 9.5, what specific convergence test are we going to be doing a lot in this section? Yeah, the ratio test. Ratio test, ratio test, ratio test. And there were 3 outcomes to the ratio test. Well, there's one. You get a limit. You do the ratio test, which is you construct this potentially nasty limit, and then you press out a number, maybe, right? And then there's 3 different outputs for the ratio test. What are the 3 different outputs? It goes to infinity, 0 or
k times absolute x minus a.
Exactly. Got it. Exactly. So let's rewind a little bit. Let's say you were just doing a ratio test on a given series. Let's say you were doing the ratio test. What were the 3 outputs for just the ratio test? 1, less than 1, or greater than 1, right? And if it was equal to 1, that's the one that gets you really frustrated, because does that tell you anything? No. If it's less than 1, you're like, yay, it converges. And if it's greater than 1, you're, yay, it diverges. So greater than 1 or less than 1 tells you something specific. Equal to 1 tells you nothing. When you run the ratio test on this, you're going to get an output that contains x. And then you're going to figure out what you have to do to x to get the things that tell you something useful. You figure out what you need to do to x to get something that's actually useful. Does that kind of match what we looked at before? Here's that general form right there. That's so important. What do you know about this a value? How is this a value referred to? Do you remember what it's referred to in the section? It's the power series something a. Do you remember what it said in the reading? We'll get to that. Centered around. Anybody get to? Okay, it's fine. It's okay. Just an added little thing. So what we're going to figure out the interval. We're going to figure out the interval around a. Exactly. So we did this before. Do you remember this? We talked about this right here. Did we talk about? We talked about it in this class, right? I make sure I copy over the right notes from the right BC Calc class. But we looked at this power series right here, and it was a power series because it was in this form. It was x minus 0 to the n, and it was 1 over 2 to the n. And then what did we look at? We looked at 2 specific x values, x equals -1 and x equals 3. And did it change whether or not this converged or not? It did, because what kind of series is this right here? What kind of series is this? It's an alternating geometric series. And in this case, does it converge? Yes, because it's going to 0. Also because it's a geometric series with a ratio less than 1. So we doubly know. We have 2 different ways to know this converges. All an alternating series has to do to know it converges is go to 0. But in this case, you definitely don't know it because the ratio is less than 1. Or the absolute value of the ratio. In this case, though, does this converge? Does this one? No, because 3 over 2 keeps on getting bigger and bigger as you raise it to successive powers. It gets bigger and bigger. So, like with limits, when you're dealing with series, you're going to have so many tests that it seems a little bit overwhelming. Like, what test do I use? The first thing you should always do when you're attacking a limit is to plug in the actual target value to see if you can plug it in. The first thing you should always do with the series, look at it as in the big picture and go, what do I know about this? Well, 3 over 2 is just going to get, the ratio is bigger than 1, so what is this thing going to do? Diverge. Diverge. Okay. Sometimes you're just going to be given the written out power series, and before you can analyze it, what do you need to do to it before you can analyze it? And by say analyze, I mean run the ratio test. You need to take the expanded form and write it in its formula. You need to write the explicit formula. So you have to be really careful. What part of this formula was the hardest part for us to figure out? Do you remember?
The top part.
Yeah, which part of the top?
The power.
The power. You have to be really careful up here. Because if you change that, if that changes by a little bit, can that completely change the convergence and divergence of a series? Absolutely. It absolutely can change it. So you literally want to start it with, okay, when I plug in 0, does the first term come out? Yes. If I plug in 1, does the second term come out? Yes. So you have to be really sure of it. You have to be really, really sure of it. So then we took a look at this right here. If we actually had one of these and we checked different values like x equals 1, when x equals 1, this whole thing summed to 0. But when x equals 2, what did we get? The alternate harmonic series, and it converged. One of the things I led off with when we first started talking about this at our last class was, what's the point? At a certain level, you must be thinking in your head, why are we doing this? Do you remember what the point was? We'll look at it and go, I have no idea. There is no way for us to deal with this, but if we rewrite it as a power series, we can deal with it. So essentially what this comes down to is we will take something that looks kind of nice and sexy, but is impossible to deal with, blow it up into something like a power series, which looks ugly, but in the ugly form, we actually have a crowbar. There is some like leverage to pull it apart, do what we want, put it back together, and get an answer. Power series will allow us to deal with things that otherwise we have no other option. No other option. Does anybody know? The series converges only for x equals a. The radius of convergence is defined to be r equals 0, meaning that's in the case where there's only when x is equal to a. So there's one specific dot. So the radius of convergence can be a specific value, or it can be a range of values. Do you remember reading that last night? It can be a specific value or a range of values. So what we specifically like to look for is kind of the third one. There is a positive number r called the radius of convergence such that the series converges for the absolute value of x minus a is less than r. Can someone read? What does that mean? If I just gave that to you in Algebra 2 right here, if I gave that to you in Algebra 2, can someone tell me what that means if a and r are constants? Cameron, what does it mean? Like algebraically, what does that mean?
The absolute, well, okay, so
It's,
x minus a is less than r, x minus a is greater than negative r.
yeah. So that means it's the collection of all what values? It's all of the values within what?
For x,
Within what of what?
No.
Yeah, you do. It's up there. Those are all of the values that are within a certain distance from another value.
Okay, within a from r.
Yes, exactly. That's just the super simplified way of saying the collection of all values that are within a distance of a from, sorry, within a distance of r from a. Sorry, I reversed that there. Within a distance of r from a. Mathematicians love to write things that take a lot of words and go like this. Have you ever seen the notation that looks like this before? You've seen a little taste of this. Like, well, x, and there exists a unique n value contained in C. Do you know what that says out loud? For all x values, there exists a unique n contained in C. I mean, that's gibberish when you say it out loud, but mathematicians, there are certain things that mathematicians say so frequently that instead of saying for all, they write an upside down A. Instead of saying there exists, they write a backwards capital E. And instead of saying unique, they write an exclamation point. So math truly is the, if you wanted to come up with like the universal language, math is it. And actually there's a small vocabulary set. Literally, there's like 150 words that if you learn in like 10 different languages or in symbolic form like that, you can understand math papers in just about any language. Interesting side note, if you go on to do a math PhD, like you do undergraduate math, you want to go on a math PhD, to apply as part of the application to most math PhD programs, you actually have to have functional knowledge of at least 2 non-English languages. Why? Why would you need to know another? Here, what the heck is this? You probably saw this and you're like, man, we get to deal with letter soup. What is this? What is this? That is the ratio test, right? So what's this thing being put up here? Right here. That's the n plus 1th term, and this is the nth term. This is what we're going to be doing. You're going to be taking the nth plus 1 term, absolute value of that, and you're going to be dividing it by the general form for the nth term, and you're going to be doing the limit as n goes to infinity and seeing what the limit comes down out to. That's all this says. This is the general form for the nth plus 1 term and the nth term. So if we want to start in the general sense, what do we not have right now for this one right now? Find me the formula right now. So do that right now. Okay, anybody have it? Anybody have a formula for me? Summation of what? N equals 0 to infinity, yep.
X of n.
X what?
X to the n.
X to the n, okay.
Over n.
N factorial. So does this work? If n equals 0, x to the 0 is 1. 0 factorial is 1. You're very good. So we do get the first one. What about x equals 1? Sorry, n equals 1. You get x to the first over 1, which is the second one, right? Because what can you say this? You can, instead of saying 0, you could call this what? X to the 0 over 0 factorial. And this is x to the first over 1 factorial. So you need to kind of like regeneralize. Sometimes does simplification help you? No, sometimes simplification makes it really hard. You will get questions on the AP test where it'll give you like the first term, the second term, the third term, the fourth term, the fifth term, and you'll look across and be like, oh, there's clearly a pattern, but like 2 of the fractions have been simplified, and you have to spend the bulk of your time like unsimplifying the fractions. Okay, same thing here. So we now have a general form for this. So what test are we going to run to try to find the interval of convergence on this, the radius of convergence, which gets us the interval? The ratio test. So we're going to do the limit as n goes to infinity of x to the what? N plus 1 over n plus 1 factorial over the absolute value of over n factorial. Yeah, so we're going to do the math out. So we do the limit as n goes to infinity of xn. Sorry, doesn't go up there. It's n factorial. Sorry, I'm going to mush it all together. We have x to the n plus 1 times n factorial over what? N plus, well, I'll keep them lined up. X to the n times what? Correct. And we have this, right? Keeps it positive. We just want to keep it positive, just in general in life. We like to smile, you know. Okay, you have to be really careful about your cancellations, right? You have to be super careful. If you cancel here and here, what do you end up with on top? X to the what?
1.
You just get x to the 1, because what do you do with exponents when you divide? Subtract. And then if you cancel this, what are you left with down on the bottom? N plus 1. So this says the limit as n goes to infinity of the absolute value of what? X over what? N plus 1. So let's analyze this for a second. Let's think about this for a second. They were...
0 and
Yeah, exactly. So you have, it blows up. It goes, so L greater than 1, L equal to 1, or L equal to 1. And what's the other one? L less than 1, right? So let's look at this. X is a constant to begin with, right? X can be any constant, right? But n is always blowing up, right? So if I fix an x value, what's always going to happen eventually? This thing, what is this thing always going to do, no matter what x value I choose? It's always going to go to what? You said it, it's always going to go to 0. If I pick x to be 7, does this thing eventually go to 0? Sure. If I pick x to be a million, billion, bajillion, what is this thing still always going to eventually go to? 0. It's eventually going to go to 0, right? Because if x is fixed, it is therefore non-infinite. You understand that little piece there? So what can we say about the radius of convergence? So this thing, we show that this limit is always going to be going to which of these 4 right here? Less than 1. No matter what, we just figured out that this thing is always going to be going to 0, so it's this one. So what does that mean about the radius of convergence? What's the radius of convergence on this one? It's infinity, right? So where does it converge? Where does it converge? Converges where? Everywhere. Everywhere. No matter what x value you plug in on this, it'll always converge. What this shows you essentially, and you can kind of have an intuition about this. So x to the n gets pretty big, right? What gets bigger faster? N factorial gets bigger a lot faster. It's not good enough to just say the bottom gets bigger than the top, because the harmonic series, does the harmonic series converge? No, it doesn't. But eventually, how big does n factorial get? arbitrarily bigger than x to the n. Does that make sense? Kinda? Okay. Okay. What about this one? This one looks similar-ish. So what's the first thing we have to do if we're going to determine the radius of convergence? What's the first thing we have to do? Find the formula. Do that right now. And then, okay, so if we do this now, what limit, write it carefully, the limit that we have to do, let's just write it all together. Well, we can write the whole thing out once. We end up with -1 to the n minus 1, x minus 1 to the n over n. But that's not in the right place, right? That's the nth one. Where do we need to put that one? Down below. And what do we put up top? -1 to the n times x minus 1 to the n plus 1 all over what? Like this. So when we do this out, we end up with n times -1 to the n times x minus 1 to the all over -1 to the n minus 1, x minus 1 to the n times what? N plus 1. Here's what I'd like you to do. Finish this limit, and then I want you to answer the question as best you can. Where does this converge? Anybody figure it out? Okay, that's fine. You think so, or you know so? Oh, come on. Okay.
-n times parentheses x minus 1 over n plus 1.
Cool. I like that. You got, so what? So say it again.
So -n
Yep.
times parentheses x minus 1
Yep.
over n plus 1.
Like this? It's the absolute value of this?
Yes.
Is that correct? What aspect of this doesn't really matter anymore?
N minus 1.
So you see this right here? You see? No, you see this right there? As n goes to a bajillion and you take the absolute value, what happens to this? What kind of effect does that have as n gets really big? It goes to what? It goes to 1. It goes to 1. Do you agree with me?
Yes.
A bajillion, a negative a bajillion over a bajillion plus 1, negative, time, absolute value, what does it go to? 1. So what does this limit actually go to? The absolute value of x minus 1. You know that a series converges when you do the ratio test when this right here is what? Less than what? Less than 1. So for what values does this converge? It converges for x values between -1 and 1. This part right here goes to 1. Are you okay with that? Please, if you're not, you need to say something now. We're good? So this limit, whatever x is, it goes to the absolute value of x minus 1. But this right here, everybody, if we want it to converge, this value has to be what? Less than 1. So if I ask you the question, for what values of x does this right here converge? What do you say? Oh, and by the way, you need to not let me make basic math errors like that. That is not true. X minus 1 has to be less than 1 or greater than -1. So what is x between? 0 and 2. Please don't let me do that again, okay? 0 and 2. So for what values of x does this converge? From all the values between 0 and 2. 0 and 2, exactly, between 0 and 2. To translate this into what's going to be valuable later, for the x values between 0 and 2, this series will be an accurate model of a different function. Because it converges between 0 and 2, it will be a good, accurate model. Right now, we're just focusing on the mechanics, not the payoff. It's a little bit frustrating. Remember when you did Riemann sums and it was really frustrating? And you're like, I hate adding all these things up, and then you learned how to differentiate after and integrate with the fundamental theorem of calculus, and you're like, yes, I don't have to do all that limit stuff anymore. We haven't really gotten to the payoff of why this is useful yet, but this is the important part.